Let's take a look at chapter 11, which is the t-test for two related samples. I want to contrast this idea of related samples with the last chapter, which was independent samples. So in chapter 10 we were looking at related independent samples, and what we had, the two groups that we were comparing, you had a control group versus the treatment group. Okay, and that's how we obtained our control and our manipulation, and that worked because we could easily separate the groups, and therefore they were independent. Okay, and so because of this independence, we were allowed to make some assumptions, and namely we were able to talk about the pooled variance. All right, that pooled variance. These were independent samples coming out of the same population. The only difference was the treatment. Therefore, the estimated, if we assume that the treatment had no effect, then we can use kind of a combined variance to estimate both individual variances. The difference though now is that since we have this idea of related, we can't make that pooled variance assumption. So the key was that they had to be independent. So because we're dealing with related samples, we can't use the pooled variance anymore. And so to get around some of the more fancy math, what we can do is use what's called a matched pairs design. Matched pairs design, and this is getting at the related idea. And so in other words, instead of having two distinct groups, what we're going to do is take, so this had a sample of, let's say, 20, and this had a sample of 20, and so collectively we had 40 members in the experiment. For the matched pairs design, what we're going to do is we're going to have a single sample of, let's say, size 20, and we're going to run two different treatments. We're going to have two different treatments. And then what we're going to do is we're going to compare the outcomes. And the way this is going to work is we're going to compare the mean from each group, each treatment. And so the idea is that since we have a single sample of size 20, the control comes because we've given each member a chance to try out both treatments, and so we can compare one treatment against another treatment if we use the same unit. And so one person here, this is person number 1, tries treatment 1, tries treatment 2, and then we can compare results. So it's kind of similar to the correlational study where you measure two things on the same person. In this case, we're going to be very careful and control everything except for the treatment, and then compare the outcomes of the treatment. And the way we're going to do that is we're going to look at the mean difference. The mean difference between the outcomes. So in other words, if you had a mean of treatment 1, so look at all of the 20 members, look at their treatment 1 average, and then look at their treatment 2 average, and then compare them by subtracting. And so the way this is going to work for our hypothesis test, we want to, let me back up. Our initial assumption for our hypothesis test is that there should be no difference. There is no difference between treatments, and that that's the same basic assumption we had for chapter 10, in chapter 10 for that hypothesis test. But here, the way we come up with that difference, instead of mu1 minus mu2 equaling 0, we just have that the mean difference. So in other words, the average of the differences, we're going to compute the differences and then take the average. We're going to say that that mean difference is 0. Okay, we're going to test that against the alternative that says that the mean difference, well, for the two-tailed test is not 0. Mean difference is less than 0 for one test, or the mean difference is greater than 0. So these are the directional tests. Okay, so let's just stick with the two-tail for now. Two-tail. Okay, so I want to run through an example. the computation goes the exact same way for any t-test, and so there's not a lot of new material here. It's just kind of a new idea that you need to wrap your head around. Kind of more or less the difference now is on how we conducted our experiment. Okay, so let's take a look here. And an example, I'm looking on page 336. This is number 12. Okay, so in an attempt to understand how masculine themed words influenced job applicants, some researchers put together two different kind of categories of job advertisements. One of them had masculine themed words, the other one had neutral themed words. And what they did is they took a group of female potential applicants, and they had, let's see, a sample of 25 female applicants. Well, not necessarily applicants, people that might be applying for a job. And they said, okay, all 25, review this job, or maybe it was a sequence of job ads, and that had masculine themed words, and give us a ranking of how likely you would be to apply for these jobs. Okay, then they said, okay, thank you, and then they gave them a new set that now contained only neutral themed words, and they asked it the same question. They said, okay, now of these job advertisements, tell us, how likely you would be to apply for these jobs, and then they calculated the average there, and so they could come up with the mean difference. And I'm going to write it like this: it's the mean of the neutral ads minus the mean of the masculine themed ads. And I'm writing it like this because they give us a bit of information. They said that the mean difference was 1.32 points, and then they give the clarification in favor of neutral ads. If it was in favor of masculine, then it would be a negative here. Does that make sense? So based on the order I have here, if you have a larger number, subtract a smaller, you should get positive. But if the neutral ranking was less than the masculine, then it would be a negative down here. So because this is positive and it's in favor of the neutral, then I know this is how they crafted their mean difference. Okay, so the way the t-statistic works is you have still degrees of freedom, and since we only have a sample of 25 and we're calculating everything based on the difference, not on the individual means, then the degrees of freedom here is still just going to be the sample size of -1. So in our case, 24. Okay, and that is going to be equal to the mean difference minus the hypothesized difference divided by the standard error for the mean difference. Now, we need to talk about this. In our case, this is just 1.32 minus 0. 32 minus 0, I'll write it out, and the mean difference. Okay, so you might be testing if the mean difference is 1 or something else, and so this might change, but for us in this book it's always going to stay at 0. So you could rerun this. If you had a hypothesized mean difference of 10, then you could rerun this with a 10 right there, and it would all work the same way. So let's look at this idea of the standard error for the mean difference. So the standard error for the mean difference is going to be made up of the sample standard, the population variance for the sample, the sample variance divided by n. So it goes the same way like the central limit theorem says for the standard error. And then this s squared, now I should really be putting a subscript of d to say it's from the difference. It's going to be the sum of squares for the difference divided by the degrees of freedom. Okay, so we're basing everything on if you had each so let's say that I was used in the study, and so I had a score for treatment 1, so Jason for treatment 1, Jason for treatment 2, and then I can calculate the difference for me, which would be, let's say, T1 minus T2, and then I can look at that for all participants. So this is the difference between the rankings, and then I can look at the average of that difference. And so we don't have any complicated math going on here. It's just the straightforward sum of squares, but it has to be for the difference. And so in our example, we have the sum of squares for the difference is given at 150. The degrees of freedom would be 24. And so that tells us that the population variance for the difference, sorry, the sample variance for the difference would be 150 out of 24, which gives you 6.25. Okay, that tells us then that the standard error for the mean difference is going to be 6.25 out of 25, and then we take the square root, so that gives us the square root of 0.25, which is 0.5. Okay, so let's run through this computation. So start to finish, our hypothesis starting out is that the mean difference is 0. Our alternative hypothesis is that the mean difference is actually not 0. We have our t for 24 degrees of freedom, which is going to be the mean difference minus the hypothesized difference divided by the standard error for that. So in our case it's 1.32 minus 0 out of 0.5. So in other words, you get a t statistic of 2.64. Okay, so our t of 24 degrees of freedom is 2.64. Okay, this is our test value. Now, if you look at the problem, it says use a two-tailed test and compare at alpha equaling 0.05. So if alpha is 0.05, we could switch over to our t-table, and we scroll down until we find degrees of freedom 24 right here. And so we would find, whoops, for our alpha, how do I get a mouse? For the alpha of 0.05, degrees of freedom here 24, alpha 0.05, it's 2.064. So alpha 0.05, 2.064. Okay, so we're to the right of this. Our number is 2.64, so we can actually make the claim that our p-value is in between 0.02 and 0.01 if we wanted to. But we're just going to stick with this t critical value and just compare like that. So what I just said was the t for that alpha, I'll keep in red here, the t for that alpha, t of 24 for alpha 0.05 is equal to 2.064. So our t is greater than that. 2.64 exceeds that 2.064. So that tells us that we can reject HO in favor of H1. And better yet, we can actually put a p-value to this, a loose estimate for the p-value, since our test statistic landed in between 2.06, well, actually it was even better than that. If we switch over here, it was in between these two, 2.492 and 2.797. So 2.492 less than our t, and I'll switch colors, 2.64 less than 2.797, and these t values corresponded to 0.02 and 0.01. So that tells us that our p-value is in between those. So we can say that our p is less than 0.02 but greater than 0.01. Okay, so if we wanted to actually put a p-value, there we go, which helps us if we change the critical value here. If we change the significance level from 0.05 to 0.01, then we couldn't reject anymore since our p-value is greater than it. So, but in this example, we're just looking at the alpha of 0.05, therefore we have enough information to reject. Okay, and I'll write this all up in a statement in just a moment. We also need to come up with the r squared for treatment. Okay, so the size of the treatment effect, so r squared, the amount of variation accounted for. Again, this is just t squared plus the degrees of freedom, and so for us this is going to be 2.64 squared out of 64 squared plus 24, which gives you only about 22.5%. So not a whole lot. We're not accounting for a whole lot of the changes, but that's okay. And also our Cohen D, I don't think we were asked to do this, but let's come up with the estimated D for effect size here, which again is the mean difference divided by the square root of this stuff. So our D is going to be 1.32 out of, well, the square root of 6.25, and you end up with 0.528. Okay, so that's our estimated effect size. So about half a point for each person, and that's that's not bad. I mean, we were saying that the mean difference was 1.32, but the difference in our treatment then is only about half a point that we can account for, which kind of makes sense there. Okay. Alright, so we're also asked to write a sentence describing the outcome of the hypothesis test and the measure of effect size as it would appear in a research publication. And so we would say that there is a significant difference in job application appeal, job application appeal with neutral words than with masculine words. And then we would report our T. Let me switch colors. Degrees of freedom 24 is equal to 2.64. I'm going to go ahead and put a p-value in here. P-value is less than 0.02. That's all we really know. Okay, that way somebody could say then we could get at least to this point and still reject. We don't know exactly how far beneath it. If you like, you can put in the lower limit, and that way you can definitely guarantee where you can reject, with D equaling 0.55. Whoops, not 55. 528. 528, and R squared equaling 0.225. Okay.